Hello everybody, welcome to Notes 8.1 and the beginning of Unit 4. We've got a new function in the house and it's called a rational function. And we're going to get introduced to this new rational function today and of course start off by seeing how to graph them. Here we have a rational function. You can see the essence of rational functions are that they have a fraction in them, and the variable x is in the denominator of that fraction. And look, it's our old friends h, k, a, and b. And just like we did with, I think it was cubic functions, we kind of simplified things by letting b equal 1. And so we're not going to mess around with b in this unit because, as you'll notice, stretching these vertically has the same effect as compressing them horizontally. So why have two parameters that do the same thing when you can just have one? So let's go ahead and take that 1 over b out of our model. And that simplifies to a 1 over x minus h plus k. And here they are now, a, h, and k. You can see here that a is 3, h is positive 2, and k is 1. So whatever's going on here, something is going to be stretched vertically by a factor of 3, shifted to the right by 2, and shifted up by 1. Well, let's see our new parent function. And this parent function, by the way, can be found on the Parent Functions of Algebra 2 cheat sheet, which you hopefully printed out back from Unit 3 at the beginning of it. And if we look at the core of this function without the a, h, and k, we just see 1 over x, and that is the OG rational function. To see what this bad boy is about, we'll just go ahead and plug in our kind of usual values for x, -2, -1, 0, 1, 2, and substitute directly here. 1 over -2 is -1/2, so we have over 2 down, over 2 to the left, down 1/2, a little point right there. When x is -1, 1 over -1 is -1, so I got another dot right there. And when x is 0, 1 over 0, that's bad news. This is undefined. X cannot equal 0. We've got a restriction on the domain, and to represent that visually, we're going to draw a vertical line with that equation x equals 0, but since I can't touch this. Since you can't touch it, that's called an asymptote, and we're going to make it a dashed line, meaning there's not going to be any points in these simple rational functions that cross that line, at least not in the parent function for this one. X can't equal 0. When x equals 1, 1 over 1 is 1. Oh, look, we switched to the other side of that asymptote now, and things are going upwards. And when x equals 2, we've got a 1/2. Well, the picture that this is painting, by the way, this is strange, but there's no way that y is going to equal 0. Look at, no matter if we kept on building this table up and up and up, 1/3, 1/4, 1/5, 1/6, 1/100th, there happens to be another asymptote for y that y is never going to reach, and that is y equals 0, or should I say y cannot equal 0. Alright, so as a summary right there, vertical asymptote at x equals 0 because the denominator cannot equal 0. Horizontal asymptote at y equals 0 because there's nothing that you could plug in for x that would make a fraction, 1 over something, become 0. It just can't happen. And so how are we going to connect these dots if we are not able to cross these asymptotes? Well, we could do a lot more points, or you could just trust me that what's going to happen is this little branch is going to get tucked into this corner and another branch up here, and just like that, welcome to your new function of the month. Let's go ahead and shift that over, and that's the easy part. We're going to do that in the same way that we've transformed every other function. We're going to take those x values in that table and add 2, since h is 2, and we're going to multiply or dilate all of the y values. We're going to stretch those vertically and add 1 because k is 1. So here I go, substituting now these x values into this little gem, adding 2, I got 0, 1, and so on and so forth. And multiplying by 3, this isn't going to be too fun. Negative 1/2 times 3 is negative 3/2, plus 1 is negative 1/2. Negative 1 times 3 is negative 3, plus 1, excuse me, is negative 2. Undefined, well, that's going to continue to be undefined right there then. And you substitute those other points. I'll do the number crunching for you. You got 10 and 2.5. So those asymptotes are going to shift over just as everything else in the graph shifted over. The vertical asymptote is going to shift over 1, 2 units to x equals 2, or shall I say x does not equal 2. And the horizontal asymptote is going to shift up by 1 to y equals 1, or shall I say y does not equal 1, cannot equal 1, will not equal 1. And look at, it's kind of sort of like a vertex right here. Over 2, up 1. That's that h value and that k value right there. But it doesn't have a name like that except for the intersection of the asymptotes. So I got the vertical asymptote at x equals h, my horizontal asymptote at y equals k. I did my table, I plot my points. 0 now, remember to go back to the origin, 0, negative 1/2, and over 1 down 2. And then that's it, just a couple of points in each little quadrant there are enough to be a guide. 1, 2, 3 up to, whoa, up 10, way up yonder, and over 4, up 1, 2.5. So that thing's coming in hot. Uh-oh, I kind of messed that up with my digital pen, but you get the idea. Just don't touch the asymptotes, just approach them and make a wider turn depending on that, how far it is from the asymptote. And notice that this thing's been vertically stretched. The original parent function would have been 1 box away from the intersection of the asymptotes, and now we're 3 boxes away in the vertical direction. So you can kind of even see that vertical stretch. And now just for the record, I think your homework's going to have you state the domain and range. It's going to ask you to do that in a number of different notations. People who are using the book, you're just going to state one of these notations. Be sure to pay attention to the instructions on the assignment sheet. Folks who are, whoops, that's Unit 4, Unit 5, and I don't have Unit 4. But on the assignment sheet, for people doing it in the book, you can just pick one of these 3 notations and just kind of vary it. And when you do that, remember set notation is curly brackets, all values of x such that, and we can just write x does not equal 2. So it's all reals except for, and this is called an excluded value. It's what x cannot equal, or in the case of the range, all values for y, be sure to change your variable such that y is not equal to 1. So set notation kind of lends itself to this, but again, in your homework, be sure to vary the notations, because you got to understand how to write that in inequality notation. We don't write x is not equal to 2, even though that would be a non-equality. Instead, we write to the left of 2, or, and be sure to put an or and not an and, because this is doing the splits, or to the right of 2, and y is less than 1 or greater than 1, just not equal to 1. And likewise, in interval notation, we'll represent those 2 branches similarly, and we put a U in the middle to represent the word union. And that's all the way from negative infinity up to 2, but look at the soft brackets, not including 2. This is how we represent that. We're going to skip the number 2, and likewise for the range up to 1, but not including 1. All right, let's do that again. Uh-oh, this is not in that form. We've got issues. Oh wait, maybe we could undistribute a -1 from the denominator, and then it would look more like x plus 2 or something with a -1 out in front of it, but no, it's just not looking right. Well, when they're pretty simple looking like this, we can change them into this form, just like we've done in other units. When they don't look right, we can do some tricks to change them into the familiar form. And the trick is to just execute this division. A fraction means top divided by the bottom. So I'm going to go ahead and here's my divisor. I'm going to do long division into 3x plus 8. It's just simple long division. And remember how that works. You look at the first term. How many times does negative x go into positive 3x? And you could just do a little scratch work even in your brain. 3x divided by negative x is -3 because the x's cancel 3 over -1. So I'm going to put a -3 up top, but I'm going to put it over here above the 8 so I can tell I'm at the end of the road here. This is the only term I'm going to need to do. Everything else is going to be remainder. -3 times negative x is positive 3x. Sure enough, that's matchy-matchy. That's good because I'm going to subtract. -3 times -2 is positive 6. And remember how this one works. I subtract the whole term, meaning I switch the sign of each one and add, in my book, 8 plus -6 is 2. That's my remainder. I have a remainder of 2. So that 2 is going to go over my divisor, -x minus 2. And this is why we express them in this way, because look what happens when we rewrite this quotient now as f of x is -3, that's the quotient, plus remainder of 2 over the divisor, -x minus 2. It might not look like that yet, but would you mind if we just rearrange the terms here? Let's just flip-flop them. That would be 2 over -x minus 2 minus 3. Oh, hey. See that 2 in the numerator? Let's pull that out of the whole deal and express it as 1 over something. And that's something, well, let's go ahead and undistribute that -1. And I'm going to apply it to the front right there. Changes that to an x plus 2. Did you see what I did there? -x minus 2, undistributing a -1, and applying that -1, popping it out of the denominator and hooking it into this initial term. Well then, we've got ourselves an A, an H, and a K. And so we can graph this. I'll skip the graphing of the parent function for this one. I've got the parent function table right up above. So I'll use that because I'm kind of out of room here. There's x minus h. Remember that h is a -2 because it's the opposite of what we see here. A lot of sign changing happening in this one. And -2 is my a, y minus 3 is my k. All right, I'm going to look up at that parent function. Let me just grab it right here to have it conveniently located. And plugging in the x's, I've got -2 minus 2 is -4, 3, 2, 1, 0. That usually flows pretty good when there's no b. And -2 times -1/2, that's 1, minus 3 is -2. That's cinchy. And when I plug in the -3, I'll crunch that. Sorry, the -1. That's 2 minus 3 is -1. And here comes my undefined. And -1 gets me a -5, and you substitute 1/2, and 1/2 of -2 is -1, minus 3 is -4. All right, let's hook up the asymptotes first. Got h was -2. And k is -3. Oops. And we make those dashed lines because they're not part of the graph. And here go my points. Sorry, I'm looking at the wrong points. Here, these points. Let me get rid of this highlight. -4, -2. And -3, -1. And there's that branch. Sure enough, it's pulled out from the corner just a little bit, just by a factor of 2. Normally, I would have expected to tuck that curve in right there, away from the intersection by 1, 1. But now it's out by 2. Oops. And my other branch, pretty much symmetric, but getting blocked down here. -1, -5, and 0, -4. That's okay. Ba-ba-da-da. And we're asked to state the domain and range pretty much always. And I'll just squeeze that in set notation real quick. Sorry, a little sloppy at the bottom of my digital writing tablet there. All right, last up, we're going to work this backwards, which we often do in every unit. Once we see how a function is graphed, we can work it backwards. Seems like hk is kind of a significant thing in every single unit that we do. 1, 2, 3, 4. H is +4 right there. I guess I just want to be consistent here. I'll say y equals 4. And x equals 3 would be the equation of this. So h and k are 4 and 3. Yeah, I had put h up there. That was wrong. H is over here. And my general function, since we're letting b equal 1 and we're controlling everything with a vertical asymptote, is a times 1 over x minus h plus k. So there's the story so far. And from there, of course, I'm going to pick one of these 2 points. I don't know about you, but I'm kind of digging on the looks of 4, 6, because every point on this curve has to work in this formula. I still don't know a, but I'm about to find it. One over -1 is just -1. Some of you on your tests, you have a tendency to make a little boo-boo while you're solving these. You've gone and added -1 plus 4 at this point. No. Take away 4 from both sides. Multiply the -1 times the a, and you'll find that a equals -2. And notice that a is negative, so it's not like something opens upwards or downwards here. But compared to the parent function, oh, wait a minute now. I think I made a mistake. Yeah, I dropped a negative, huh? This should have a positive a because the branches are in the top right corner, quadrant 1, as we call it. And quadrant 3, that's when a is positive. That's where we expect it to be. And in this one, I can see from the beginning that a should be positive also. So kind of a good mistake to make. Uh-oh, right? Did something wrong. And, geesh, what did I do wrong? Oh, yeah, how about this? 4 minus 3 is not -1. Was anybody thinking that out there? Yikes. Still, don't add the 1 to the 4. This is just 2 equals a. And yeah. All right, final answer. The equation of this guy up above is 2. 1 over x minus 3 plus 4. That's the way. I like it. Go get assignment 8.1. Good luck.